I'll share you the presentation. Can you see the slide?
Yes, sir.
Yeah. So today we'll discuss about earth pressures. Uh, do you have any idea about earth pressure? Both of you? Any one of you?
uh, give vertical loads. Uh,
What?
they can create pressures in the land.
Okay. So have you heard this in your soil mechanics subject anytime? Or this is the first time you are listening? Have you heard this word, earth pressure? Harini or Binoy?
Yes, sir. Actually, our pressure is the lateral component of the vertical pressure which is exerted on the soil.
Come again, come again.
It is the horizontal component
Yes.
of the vertical pressure that is exerted, of the overburden pressure at
Okay.
any level.
Okay, that's fine. So, so then you can see, right, the slide. If you confirm, I'll just go ahead now.
No, sir,
You can't see the
not
slide.
now.
Okay, okay, okay.
Yes.
Let me share now.
Yes, sir.
Yeah. So earth pressure is nothing but it's the pressure, horizontal pressure from the soil on a structure. Okay. Now, see, generally retaining walls. Let us introduce retaining walls. Okay. So, what are retaining walls? Retaining walls are generally supporting structures for embankment or vertical cuts. Suppose you see a hill, there is a hill, let us say. Now we want to go to the peak. Then there will be this road. There will be a route, right? So that route, if you see at one side, uh, if you see one side, how does it look? It looks like, what do they do? There is hill, then there is a road, right? Then so again there is a road, fine, and there is again there is a road. So suppose this is one side of the hill, other side, before these roads are laid, this was the structure. This is the left side. So left side is the original hill, right side is the hill after making the roads. Now, when you are cutting this soil, you are cutting this much soil. Let us say this is the soil you are cutting to make one horizontal road. So after cutting, it will fall, right? This soil will fall. So to avoid that fall, you need to construct a vertical wall throughout. Okay, suppose if it is, you can say um, there is an embankment. Let us say, okay, so like this, longitudinal. Okay, now, if you want to construct a retaining wall, the retaining wall will be like this to support this soil. So the retaining wall will be longitudinal. But here retaining wall may be some round. because this hill is in circular shape if you cut any horizontal cross section. Okay, so now there should be a wall here so that the fall of soil will not happen. So then this is the road, like that. Somewhere again you will construct wall like this to avoid. Now suppose you need, let us say, yeah, at this point let us do this to avoid this fall. We have constructed retaining wall. Now there is no retaining wall requirement here, let us say this portion, because this is natural slope. But suppose this road is not enough, what do you want to do? Then what will you do? You will increase by pouring another soil here. But if you pour soil, what will happen? Again it will fall down. In that case, again what do we do? Again we will construct a wall here, then we will fill the soil here. Okay, after filling the soil, then you can get the wider roads. So to get the wider roads, so you fill this gap so that you will get the wider road, as well as to avoid the falling of soil. So for all these kind of requirements, you go for these kind of vertical structures, vertical walls. The walls which are retaining the soil behind the wall is called retaining wall. The walls which are retaining the soil. Okay, so like that. Now here also the slope is like this. There it can be anything, right? There is a road, so then they will again construct a retaining wall here, from here to here. So you can widen the road if you want, or else they will construct up to here. They don't construct this part. Okay, up to construct, because this is natural slope. This will not fail. This is vertical, that's why they have constructed a wall so that they can use this road. So that this is the retaining wall. Now, so retaining walls are subjected to, now I'll just draw retaining wall. Okay, this is the retaining wall. Now I'm talking about side view. So retaining wall can be like this. Okay, so its length. So now there is soil behind it. Okay, there is soil behind it. So this is the ground level, there is a soil, this is another ground level, this is also ground level 2, you can say ground level 1. So this side there is nothing, this side there is a soil. Okay, soil is nothing but, this is what, earth material. Okay, this is earth material. Now this wall should not fall down, right? See, because of this soil, because of this soil, what happens? This soil will push the wall in this direction, right? When it is pushing, it should sustain those loads. That's how the retaining wall is designed. So when it is trying to sustain, just a minute, just a minute. So this has to sustain these loads which are exerted by this soil. So soil will exert pressure in this direction, right? It cannot exert pressure in this direction, of course, because soil is behind it, so it will push the wall in this direction. Now this pressure whichever is coming from the soil is nothing but earth material. That's how the pressure which is exerted on the wall is called earth pressure. Okay, this is called earth pressure. Okay, so there are different types of earth pressures existing. So one of them is active earth pressure. So I'll use just EP. Okay, whenever our earth pressure is coming, I'll use shortcut EP. Okay, then passive earth pressure, passive earth pressure, then at rest earth pressure. So what are those? Now, situation, general situation, as I explained, okay, general situation, sorry, general situation will be there is some earth material here, okay, this is earth material. What happens now? Earth material will exert this kind of pressure, okay. Now, if you don't want this wall to move, of course, because of that pressure, wall tries to move this in this direction, okay, this is it tries to move in this direction. If you don't want this wall to move even by uh, any amount, suppose you want this wall to be at rest, that means you don't want it to move, that in at that condition when it is not moving, this wall, the whatever the pressure is exerted on this wall is called at rest pressure. At rest pressure, suppose you can see the bridge, okay, there are some bridge, suppose there is a bridge, okay. Now these are the ends, two ends, there are some columns, piers, right? So now they are ending it. Why they are ending at this point? Because there is natural earth here, there is natural earth here, so there is water here, let us say there is water, there is again there is earth material here. Now what do you do generally at this point? We will construct a wall, a wall around this, okay. You might have seen this is earth, so there is a wall at this. To avoid this material, earth material, fall from here to water, we will construct a wall here, okay, like this in arc shape, or it may be in the longitudinal direction. So there is a wall in this direction so that this earth material will not fall in this water. So this wall is designed in such a way that this wall will not move at all. This is at rest position. So when the wall is designed not to move, okay, at that time whatever the pressure which is exerted by the earth is called at rest pressure. So you may get doubt that who wants this wall to move? Everybody wants wall to be at rest. Then we have only at rest pressure. So this is one type of pressure. So you may ask, now I will tell you what is the another condition. So there is always some permissible limit when you are design some, okay. Suppose this is the retaining wall, then this is some earth material, okay. When we are allowing this wall to move by some amount, so that the soil whichever is backside of this wall, this are by the way this is also called as backfill, also earth material, okay, also soil, okay. But generally people use backfill because it is filled backside of the retaining wall, okay. Why it is back? Because it is moving in this direction. Then that's the reason, as the soil is as the soil is behind with respect to the direction of movement, because of that you can say this is at the back side of the wall, so that is why it is backfill. Now when you are allowing this wall to move by some amount, so that whatever the soil is there will not uh, fail. It should not fail, as well as this can move. So there is a permissible limit. It can be rotated by zero point 0.3 degrees or zero point 0.1 degree. Okay, these are the permissible limits for this wall. Now, so you can ask why this soil will fail. What is the failure of soil? You may ask. See, one thing you should remember, that soil will always fail, or you can remove this will, because it always fail. We are talking about that soil always fails in shear. See, whenever you take some soil sample, if you apply compression, okay, from all around, it will not fail. Equal pressure, I'm saying. If you are applying some different pressure from here and from here, because of that, some shear stresses will develop along some plane. When the shear stress develops along that plane, because of that shear stress, it fails. Soil always fails in shear. Why? In casual terms, you can say, suppose there are some soil particles, you can say. So these, see, to give you a simple example, suppose you take a biscuit. Okay, suppose if you just apply some pressure, if you just press with the hand that biscuit which is on the table, let us say, it get it gets crushed. Mm. That is what failure. But when you come to the soil, if you take solid particle, single soil particle, okay, if you apply compression, then also it crushes. The problem is, when you take the whole soil sample, before this crushing happens, when you apply compression, let us say compression only, but different. This is, let us say, this is sigma 1, this is sigma 3. Because of the difference in these normal stresses, what happens, before the crushing of the particle happens, some the part of the soil, you can say, part of the soil, some few number of soil particles will try to move in one direction, and another particles will try to move another direction. Okay, so when they are moving in different directions, before they crush, what happens, there is a crack forms within the soil. Suppose this part is moving this direction, this part is moving in this direction, then what happens, there is a crack develops. When there is a crack is developing, if this is the ground level, if there is a structure here, there is a building, let us say, okay, when this part of the soil is moving this direction, this part of the soil is moving this direction, what happens, this structure will collapse. So that means, before the crushing of the particle, before the compressive stress reaches its compressive strength, it will reach, by the time the shear stress would have reached its ultimate level. Okay, that is the case. That is the reason why it always fails in shear, not in the compression. Before reaches its ultimate strength, it would have reached the shear stress between the particles. That's why the two layers will move in different directions. So that is one thing. First of all, soil fails in shear, and soil fails. Soil can fail. When the soil fails, the structure which is above it will collapse. Now, see, this soil is there behind the retaining wall because of the many purposes. See, we only put this soil here. We only made this structure. It may be the road, it may be some road, or it may be ground where you want to construct a G plus 10 story building, anything. It may be some oil structures, anything. So it is taking some load at the end. Fine. Now, when it is taking the load, it can fail. The soil can fail. So now, coming to the point, just before failure. So failure can happen because of the tension, because of the compression, whatever. Finally, it will fail in the shear, but the load can be compression or load can be tension. Suppose uh, mm, you can say I'll just, so there is a bowl. Okay, there is some sand inside it. Okay, now you are putting some block, a wooden block you are putting here. So wooden block can stay on the sand. This is the bowl. This is the wooden block. Now it is staying on this. Okay, without any issue. Now suppose there is a hinge here. Now what do you want to do? You want to open this side of the box. This side of the box you just want to keep it horizontal. Okay, now it is in this direction. You just moved it. Then what happens? This soil will flow down. Then this wooden block collapse. That means because of the movement of this wooden block is collapsing. Because why? Because of the sand which is failing below that wooden block. So you may not need this much of movement from here to here 90 degrees. Even by 2 degrees or 3 degrees, this would have already failed. This collapsed. That means the shear stress has reached shear strength of the soil along one plane, any plane. So that is the thing. So now uh, I'll just erase it. We'll take, now as we come to the point of earth pressure, what happens when the wall is allowed to move in this direction? Now there is soil tries to move in this direction. So when it is moving in this direction, there is a total soil sample along above one plane. Above one plane tries to move in this direction, whereas this soil will be intact. That will not move any direction. Because of the continuous movement of this wall, this soil will move continuously. Then there is a plane along which the failure happens. Because of that, structure will collapse, which is above this soil. Now this plane has the angle 45 plus pi by 2, where this generally we can call it as phi also. This is the angle of friction of soil. Okay, so I will introduce two terms now. You may not have heard this. There are two. So now we have talked about soil fails in shear. That means we have to find out the shear strength. Okay, so to find out shear strength you need some parameters. What are those? There are two shear strength parameters for soil. One is cohesion, which is denoted by C. Another one is friction angle or angle of friction. You can write friction angle also. Friction angle, that is phi. So these two are the properties of the soil. Cohesion means the bond between two particles. Okay, they are bonded together, bonded because of the cohesion, attractive forces. You can say. Okay, another one is friction angle. Friction angle is nothing but this is one of the parameters which in which we try to tell about the frictional resistance. Suppose there is a block which is on the floor. If you want to move this in this direction, you need to apply some force. How much force? You need to apply the force which is greater than the frictional resistance between this. So that's how, if you take soil, if you draw a line or anything, so this soil sample, if they are moving in different directions, the friction between these soil particles is denoted by friction angle. If it is having more friction angle means it is having more frictional resistance. That is, finally it has more shear strength. So that's how you just you just describe the shear strength in by using these two parameters, cohesion and friction angle. So friction will be there generally in the sands. Sands will develop shear strength because of the friction between the two particles. That's why they possess friction angle. Sands. I'm talking about sands. Suppose if you take clay particles may not have friction between the particles. It may be zero sometimes, but they have cohesion. They have some attractive forces between that. So you can feel that clay when you take that. Okay, that is measured by cohesion. So this is clay. You can say clayey soil means cohesive soil. Sandy soil means friction soil. These are frictionless soils or cohesive soils. Friction soils or sandy soils. So that's how we divide soil into two different materials. So now you know two different parameters which can describe the shear strength. So some soils may have both C and Phi. Some soils may have only C, only Phi, anything. So combination is also possible. Now, if a soil is having some friction angle, or it may not be having, whatever. So the failure of the plane, the angle of the failure plane, when the retaining wall is moving in this direction, that angle of the failure plane is 45 plus phi by 2. If it is clay, then we know phi is 0, then angle will be 45 degrees. If it is sand, you should know what is phi, then you can find out what is the angle of failure plane. When the wall is moving in this direction means you can just mention it as away from the backfill. Okay, away from the backfill. Now, this is how failure happens. Just before failure happens, the pressure which is exerted by the soil on the wall when when the wall is moving away from the backfill is called active earth pressure. Okay, we know what is active pressure. At rest pressure. At rest pressure means when the wall is not moving, the pressure which is exerted by the wall. Now we are talking about active earth pressure. Active earth pressure. Okay, active earth pressure is the pressure which is exerted by the soil at failure, just before failure happens, when the wall is moving away from the soil. That is called the definition of active earth pressure. Okay, now I'll just, okay, this is soil. So when wall is moving away from the backfill, the pressure exerted by the soil just before the failure is called active earth pressure. This is active earth pressure. So what is passive earth pressure? This comes next. Okay, so this is second. This is the third type of earth pressure. First one is at rest. So you can just say reverse. When the wall is moving away from the backfill, the pressure exerted by the soil at failure is active. When the wall is moving towards the soil, okay, when the wall is moving towards the soil, okay, this direction, then also soil will fail. Don't think that it is moving this direction. Okay, soil may not fail. It will fail because this one part of the soil, some part of the soil, it is completely pushed continuously because of this wall. When it is completely being pushed, this total wedge, okay, above this line, you can say above this plane, this total wedge tries to move up, leaving this part down. So then also that means there is a failure plane happens. So when in passive earth pressure, this angle is 45 minus phi by 2. Okay, 45 minus phi by 2. This angle. So you can ask what when is this condition is when can this condition happen? So wall cannot move on its own. Here you can understand at least there is a soil, it is pushing. Because of that push, it is moving in this direction. We are allowing some movement, but we can't allow totally because soil will fail. So we will allow the movement just before its failure. Till then it can move. After that it should stop. So according to that, this wall is designed. But what about this? How this wall is moving in this direction? Okay. In that case, you can say, so I'll just draw, suppose this, there is a wall, there is a soil, definitely. So this, okay, there is a soil, right? But if the soil is on both sides of the retaining wall, okay, I'll just, there is a retaining wall. Now, there is a soil here. Soil can be on other side also, right? To maintain different levels, there is a soil here. Now, because of this soil, it can move in this direction. Okay. When it is moving in this direction, what happens? Compared to this soil, means with respect to this soil, wall is moving towards the soil, towards the soil, with respect to this soil. With respect to this soil, it is moving away from soil. So whatever pressure is coming from this side is active earth pressure. Whatever pressure, if suppose what happens when the wall is moving, what happens? Again, here also there is a pressure from the soil because you are pushing it. So this pressure is called passive earth pressure. Passive earth pressure. This pressure is called active earth pressure. Okay. Now, any one of you, you can tell me which pressure. So, pressure relation between three pressures. Now, I have told you about active earth pressure, passive earth pressure, and at rest earth pressure. So, you can tell me which is greater among this, which is lesser, and which is in between. So, you can give me the. So, I'll give you. Yeah, you can just tell which is minimum pressure out of these three pressures. At rest, passive, active. It is common sense question. It is nothing technical. All are before failure. See, active earth pressure, sorry, at rest is not at the failure. Definitely, soil will not fail in this condition. Soil will try to apply some continuous pressure. Okay, you are not allowing wall to move in any direction, so soil will be stable. But there will be some pressure. It's like you are carrying 10 kg weight, but you don't fail. You are continuously carrying it. Okay, you don't fail, but you can carry it, but you are still feeling that 10 kg pressure. That is nothing but at rest pressure. Soil may not be failing at this pressure, but it is there is some pressure. At that place, wall is not moving any direction. In this case, wall is moving away from the soil, moving at one point is before soil fails, the pressure is active, and this is also this is moving towards the soil. Okay, from the rest position it is moving towards the soil. So at one point soil fails. Just before it fails, what is the pressure exerted by soil is passive earth pressure. Can one of you tell me which pressure is more? Somebody told passive is greater than at rest is greater than active. Yeah, is there anybody else who can tell whether it is correct or not at least? Okay. Anyway, nobody is replying. So, Binoy, your answer is correct. Can you explain how?
Sir, when the wall is going away from the backfill,
Okay.
uh, it is actually means uh, uh, it will experience it will exert less pressure on the wall. But when it
Okay.
is getting pushed towards
Okay.
the backfill, it will definitely be. I just guessed out of visualization.
Yeah, that's good. That's good. See, now wall is not moving. Let us say there is some X pressure is coming. Okay. You can see the slide, right?
Yes, sir.
Yeah. So when the wall is not moving anywhere, the pressure exerted by soil is X, let us say. Now wall is moving in this direction, okay, away from the soil. What happens? The pressure releases because you are releasing the pressure, of course. Okay. So when you are releasing the pressure, so the next pressure will be less than X, obviously. Okay. So if the at rest pressure is X, when wall is moving away from the soil, just before failure, whatever is the pressure from the soil is, that is less than X, because you have already released some amount of pressure which is there when it is not moving. That's why active is less than at rest. Now at rest pressure is X. Now wall, you are moving wall in reverse direction, right? uh, the pressure is acting in this direction. If wall is also moving in the same direction, then pressure gets released. But when it is moving in the different direction, what happens? You are giving pressure from your side. That extra pressure will be added to the X. So that is passive earth pressure. So now active will be lesser than at rest, and it will be less than passive. This is the order of magnitude of pressures which are acting on the retaining wall. Now how to find them is the next question. How to find active earth pressure, passive earth pressure, at rest earth pressure. So you must be knowing, before this you should be knowing about the Morse circle. Have you studied Morse circle? Anybody?
Yes, sir.
Okay. So which year you are in, Binoy?
Sir, I have actually completed my BTech
Okay.
already.
Acha, acha, fine, fine. So rest of you, you can, Amit and Harini, you can tell which year you are in. Amit, are you there? Final year. Okay. So you must have heard about Moore circle. See, now I can give you a brief introduction about Moore circle. See, when you take an element from anywhere, from the soil, from the beam, from the concrete beams, columns, anything. So when you apply some pressure on it, okay. So if this pressure is sigma 3, this should also be sigma 3 because equilibrium. If this is sigma 1, it should also be sigma 1. That's how element is subjected to different stresses. So the thing is, whenever you take any plane, if the plane is acted by only normal stresses, normal stress means perpendicular to the plane. If it is subjected by only normal stresses, if there is no shear stress on that plane is called no shear stress only normal stress. These are called principal plane, the plane on which no shear stress and only normal stresses are there. Those are called principal planes. Okay, and the stresses, normal stresses which are on the principal planes are called principal stresses. Now, if, if you take any element, there will be two planes. Those two planes are perpendicular to each other. There will be always two planes which are principal planes on which there will not be any shear stress. So let us say take this element. This horizontal plane is one principal plane, vertical plane is also another principal plane, because there are no shear stresses on these planes and they are perpendicular to each other. So always there will be two planes which are perpendicular to each other which do not have shear stress. So out of them, whichever is uh, having more normal stress, that plane is called, if sigma 1 is greater than sigma 3, let us say if I'm telling this plane on which sigma 1 is coming, this is called major principal plane. Major principal plane. The plane on which minimum normal stress and no shear stress. That is called minor principal plane. Minor principal plane. So these are the element condition. Now, what about the different planes which are at some angle with respect to horizontal or with respect to vertical? Okay, there are some angles. So you take any plane. Now I'll draw a big element. Okay. So according to this diagram, if this is sigma 3, if this is sigma 1, what about the plane which is at an angle? Some theta, theta 1. So on this plane, there will be some normal stress. Okay, some sigma, you can write sigma theta, and there will be some shear stress. The shear stresses are denoted by tau theta, theta 1 you can say. And if you take another plane, okay, on this plane also there will be some normal stress, sigma theta 2, let us say this is theta 2. There will be some shear stress, tau theta 2. So here what is Mohr circle? Mohr circle, I can, the circle is drawn, normal stresses versus shear stresses. Okay, I'll give you a element. Okay, and I'll tell you I'm applying some sigma y here. I'm applying some sigma x here. Okay, there is some value, shear stress value here, tau xy. So for the, see, there will be always couple for the shear stress. It cannot happen just like that. So this will be tau xy. So if this couple is in clockwise direction, to make it equilibrium, there should be another couple that should be in this direction. This is also tau xy and this is also tau xy. See, shear stresses on any plane, suppose if you take perpendicular plane, two perpendicular planes, they are equal to each other always. Any two perpendicular planes, shear stresses will be equal to each other just to make it equilibrium. Okay, so now tau xy is same. So this is sigma x, now this is sigma y. So you know the stresses which are applied on this block. Now you don't know what are the stresses on different planes. Okay, on different planes in this element. And in this element, there will be two planes. Those are principal planes. One is minor, one is major. On those two principal planes, there will not be any shear stress. Suppose if the given element itself is vertical horizontal planes are directly major principal planes or major principal stresses, then there is no issue. But if the given element is having some shear stresses, somewhere in between this vertical to horizontal, there will be two planes. One is minor principal plane, major principal plane. Anyway, so now every plane has two stresses now. Point one is every plane has two stresses. What are they? One is normal stress, sigma, normal stress, sigma. Another one is shear stress, tau, right? Sigma, tau. You take any plane, sigma, tau. Tau may be zero, but there will be, you can write, uh, there are only two planes where taus are zero, but remaining every plane, all the planes are having some value of tau and sigma. So if every plane has tau and sigma, if you want to find out tau and sigma, it's like point. So I want to find out sigma comma tau on every plane. So in that case, what can I do? If I suppose there is a point here, there is a point here, there is a point here, like this. This point is nothing but some sigma 1 comma tau 1, sigma 2 comma tau 2, sigma 3 comma tau 3. If I can relate these points to the stresses on every plane, then what will I do? I'll take all these points from every plane. Every plane has some sigma tau. So I'll collect all those points. Then I will just put in this uh, quadrant. Then I can get some points here. I will collect from it. Those points will not be random. You should, that is the case of uh, material which is subjected to any kind of stresses. Okay, that will always be forming. So if you collect all those points, if you put in this quadrant, that will form a circle. Okay, actually you can complete this circle, but I'm just drawing only one side. Okay, only half circle. How this bottom portion of the circle will happen? See, if you take clockwise as positive, automatically anti-clock will be negative. So negative tau, you should go down. Okay, and circles can be like this. Circles can be left side of this. It is just based on the signs of stresses. If compressive is positive, then it will be first quadrant. If the tension is negative, it will be second quadrant. If the sigma x is positive, I mean if the sigma x is compressive and sigma y is, let us say, tension, then one point will be here, one point will be that side. Just that. So I'm this. So now if you collect all the points from this from every plane, so if you put, so you will get a circle. This circle is nothing but Morse circle. Okay, now there is one more thing called, just a minute, there is one more thing called failure envelope. Failure, more Coulomb's failure envelope. Okay, generally that whatever we study in our soil mechanics, that failure envelope is derived by more Coulombs. First it is developed by Coulomb, then it is modified by Moore, so that's why it is more Coulomb failure envelope. So what does this failure envelope tell you? Now you should understand, suppose if there is a block on the floor, if you have to move, if you have to apply, let us say, uh, 10 Newton force on this, so block is moving, then let us say it is moving. So then what did I do? I just put one more block here above this. Can you move it just by using, this is the minimum force required, okay? Let us say this is the minimum force required to move this block is 10 Newton. You are able to move it. But now I have put another block here above it. So will you be able to move this total structure, whatever two blocks, by using 10 Newtons? Yes or no? Can you move these two blocks together by using 10 Newtons, which is the minimum force required for one block? Can you move it in horizontal direction? Can you tell me yes or no?
No, sir.
Why?
The static friction will be more.
Yeah, good. So it is nothing but, see, this frictional force is arised by this normal force. Frictional, let us say F, I'll denote it by. Frictional force is nothing but, frictional resistance is nothing but friction coefficient mu multiplied by, friction coefficient means between this surface and the block there is a friction coefficient, that is mu into n is nothing but you can say w, that is better. W is the weight of the block, this is the friction. So if the weight of the block is w, if you multiply it by mu, then this is the frictional resistance which it can offer. Okay, so you have to that was 10 now initially. Because of this, let us say mu is zero point 0.5, w is 20, so you got 10, so you applied 10, it is moving. But now if you put another same block, the total weight will be 40 now, so total frictional resistance will be zero point 0.5 into 40. How much? 20. So if you apply 110 Newton, it cannot move. It is just common sense also. When you are increasing the weight, you cannot move. So always you have to remember that frictional resistance or shear resistance or shear strength. Okay, these are all same. Shear strength. These are all dependent upon normal force or normal stress. Normal stresses. Okay. In the same way, in the soil also, when you are applying more normal stress on any, or if you are applying more compressive stress, force on any soil sample, it needs more shear stress to fail. So that means shear strength is the function of normal stress. So if the normal stress is increasing, shear strength will also increase. You need to apply more shear force to fail it. So that's how you can say, if the shear strength is denoted by S, it is function of normal stresses. Okay, shear strength is also in terms of Newton per mm square or Newton per meter square. It is nothing but Pascal, okay, kilopascal, anything. So function of normal stress, this is also kPa or Pa, whatever. Okay, so shear strength is function of normal stress, which we understood now. So shear strength will not develop only due to the normal stress, it will also develop by cohesion. Cohesion. Okay, it will also develop by cohesion. See, now see how is this related? S equal to function of sigma. What did we tell just now about the block? F is nothing but S, right? Shear strength or frictional resistance. Now in that case, S equal to mu into normal force, okay, or you can say S equal to mu into sigma, right? That we understood from that analogy. Now this, what is this mu? Mu is nothing but tan theta or tan phi, frictional coefficient. This is frictional angle. If you take the tangent of the frictional angle, you will get the frictional coefficient. So now you understood this. S is function of tan theta, tan phi. Okay, function of tan phi. So somehow friction angle is involved. So this relation can be useful for the sands because from that analogy it is related to tan phi. Sands will have friction angle. But what about clays? Clay also has some shear strength, but it does not have friction angle. For clays, friction angle is zero, but still it has some shear strength. That means shear strength is not just a function of sigma or tan phi, it is also function of C. So Moore Coulomb equation will be nothing but shear strength is equal to C plus sigma tan phi. This is the equation to find out shear strength of any soil. If you know the C, if you know the friction angle, you can find out the shear strength of the soil. So now C is cohesion. I introduced already. I introduced friction angle also. So if you apply some sigma, if you know the friction angle, sigma into tan theta is nothing but mu. So mu sigma, see here, is shear strength. It's not just equal to mu sigma. As it is clay, as it is soil, it's not just block. As it is soil, it has some cohesion. The cohesion is nothing but C. So now that is the reason why these two are called, the C and phi are called shear strength parameters. Okay. Now if you draw in a graph, okay, so it is looking like this is y. Let us say cohesion is constant. Okay, it has constant value cohesion. Sigma is let us say this is x. Okay, tan theta, tan phi. Tan phi is nothing but, if you take it as tan theta of theta, where theta is the angle of line, tan theta will be slope of the line. So the slope of the line is generally denoted by m. So if you put, if I just convert this equation to this, y equal to mx plus c, it is nothing but a straight line which is having the intercept which is equal to c on the y-axis. So I'll just draw that. So there is y, x. Okay, this is x. Now I will draw a line. If this is c, y-intercept is c, and this angle is theta. Okay, mm, then this equation is y equal to mx plus c. Okay, then what will I do from this? I'll take it as cohesion, that is also c. Okay, I know the equation. What is the equation? C is equal to C plus sigma tan phi is the equation of the shear strength. Okay, now this is, I'll take it as sigma, I'll take it as shear strength S or tau. Okay, so I'll take it as cohesion. Okay, this is cohesion. Then I'll take it as this angle. If I take it as phi, then it's over. Now S equal to tan phi. M is nothing but tan phi into sigma, tan phi into sigma plus C, cohesion. So that's how shear strength is a straight line. Okay, shear strength equation is a straight line whose intercept on the y-axis, on the shear strength axis, is cohesion, and whose angle is friction angle. So if you can develop this line, okay, then from that line you can find out angle, that means friction angle. You can find out cohesion. Then by using those two, you can find out the shear strength. So okay, now if you apply this much sigma, okay, this much sigma, so what is the corresponding shear strength? Corresponding shear strength will be this much. Like that, if you apply this much sigma on the soil sample, okay, the corresponding shear strength will be this much. You need to apply this much shear strength, shear stresses to or shear stress only, you have to apply this much shear stress to apply, sorry, to fail the soil. So that's how this is telling about the strength of the soil. This is telling about the failure at stresses at which failure will happen. So that is the reason why this total line is called failure envelope. This total line is called failure envelope, and this failure envelope is given by this equation. And also we have studied about the Mohr circle. Mohr circle is also drawn between sigma and tau. I told you how, what are those. Each point on the circle is denoting, each point on the circle is denoting the stresses on every plane. Okay, in the soil sample. Okay, now if I combine those two, if I combine those two, suppose this is the Mohr circle. Now if now this Mohr circle of a sample one, sample one. Now the sample one is subjected to these kind of stresses. Okay, these kind of stresses. Now what can you tell? So every stress, uh, every combination of stress, you take this point, they are well within this failure envelope. That means the soil sample will not fail. So when you are increasing the pressure or stresses on the soil sample, let us say sigma y is increased, sigma x is also increased. Because of that, the stresses on every plane will increase. When the stresses on every plane is increasing, then you will get new Mohr circle at every stage of application of the load. So when you are increasing the load or when you're increasing the stresses, though, because of that, all planes will show different stresses. So at one point of application of uh, certain stresses on that, so this Mohr circle will be reaching this failure envelope. Only one point will reach, not all the points. Okay. So whenever it is moving and at one point it is touching this failures, whenever it is touching this failure envelope at one point, that one point is nothing but one plane in the sample. So that plane has reached these stresses. These stresses are nothing but they have reached their ultimate point. So if you try to increase, then at that point only this will fail. That means the soil will move down this and this will move up, or this move this direction and this will move. So along this plane, this failure will happen. Soil will fail. So at the failure, if you draw the Mohr circle, that Mohr circle will touch the failure envelope at one point. Okay, whenever the Mohr circle or the state of the sample, that is denoted by Mohr circle only. If that is well below the failure envelope, that is safe condition. So this is all about the Mohr circle. So I will use this concept in earth pressures. Okay, in the next class. So this is all about today's class. Do you have any doubt? So else I'm closing the session.
Thank you, sir.
Okay, thank you. We'll meet in the next class.